Alright, this is a lecture video about Chapter 10, which is on rotational motion and rotational energy. And we're going to see several new equations pop up in this one. So first off, when we talk about things rotating, rotational objects, we think about things going through, let's say, 360 degrees. So our angle would be from this positive x-axis, how far it's moving, measured in degrees. So theta is the angle that's measured from this positive x-axis. And it's given in units of radians, which is dimensionless. Now we can convert between degrees and radians because we know there are 360 degrees if we have we can convert between degrees and radians because we know that one whole revolution is 360 degrees, which is 2 pi radians. So you can use this to convert between radians and degrees. And by convention, if theta is positive, we say that it's counterclockwise, which means we'd be going this way. And if it's clockwise from the reference line, that would be theta, in that case, would be negative. Now our arc length, which is along here, is measured in radians, and we can convert between our angle and our arc length by taking the radius times whatever that angle is, and that would be telling us what our arc length is. And before we go on any more, this conversion you are going to be using in 10.2 because they're asking you to convert, I think, between radians and degrees. Now our definition of angular velocity, and my angular velocity is this W kind of looking symbol. That's omega. And omega is the change in your radians divided by time. And so then it's radians per second. So in that case, if this is what my initial was and this is my final, this would be my change. And sometimes you'll just see that as seconds to the -1. So angular velocity would be radians per second, like how fast it's revolving. And that's going to be different than, let's say, linear velocity. If we want to find the period is capital T, and that's the time for one whole revolution. And our period would be given by 2 pi, because that's all the way around one circle, divided by the speed that it's going. And that would tell you the time for one revolution. And that's going to be in seconds. Now the definition of angular acceleration, now we're kind of using that symbol that looks like a fish. That is equal to my change in velocity over time. So just like regular acceleration is change in velocity over time, it's going to be my change in my angular velocity over my time. And it would be radians per second, or radians per second squared. For tangential acceleration, we use like meters per second squared. And we had some in your assignment where you're asked to find angular acceleration and angular velocity, and I think this one is probably 10.4 maybe, something early on. Alright, if the angular acceleration is constant, then we can say that the initial angular velocity plus my angular acceleration times my time is going to be equal to my final. And that should look very familiar. We're talking about velocities here, except they're angular velocities. So VF equals VI plus AT. But when we're dealing in angular, our velocities, we're using this omega. And for our accelerations, we're using that symbol. Which means that all of our equations that we've had in the past, we had VF equals VI plus AT. And then we had distance is VIT plus 1/2 AT squared, and VF squared equals VI squared plus 2AD. All of those same equations we're going to see again in terms of omegas. So we had this one, it's the same as this one. And then we had our equation, which was this, which was distance equals, we had VIT plus 1/2 AT squared. So that means this one's going to be theta is equal to our angular velocity times time plus 1/2 our angular acceleration times time squared. And then this one we had VF squared equals VI squared plus 2AD. This is the same thing except in terms of angular. This is my final, my initial, and then this would be 2, my angular acceleration, and then my change in my angle. So all of those are going to be coming back. And you are going to be using those on several of the assignment questions, like 10.20 and probably, I think it's 10.36 and 10.16. Several of those are using that kind of relationship with those equations. Now the tangential speed of a rotating object, our tangential speed is going to be equal to my radius, which was how far I'm out, times my angular speed. And those units would be meters per second. So I can use this to go back and forth between tangential speed or linear speed and angular speed. And that's going to be used in 10.32 and 10.48. You're both doing some conversions. And in terms of centripetal and angular acceleration, centripetal acceleration is radius times my velocity squared. And when we had it before, when we had linear, we did v squared over r. So this is what it would be in terms of angular if I wanted the centripetal. And this is going to be used in 10.9. The tangential acceleration of a rotating object is radius times the angular acceleration. Just like we said for that, if we wanted the linear, the tangential velocity, we took r times omega. Here, except it's in terms of acceleration. So we always multiply by the radius. And then that would be meters per second squared. And tangential versus centripetal, this is tangential, and then this would be our centripetal. So be cautious if they're asking you for centripetal or tangential. All right, this merry-go-round has both tangential and centripetal acceleration. So in this case, we can see our centripetal is the one towards the center, and then we see this acceleration as it's speeding up, the tangential acceleration. All right, now if an object rolls without slipping, there's a relationship between the tangential and the rotational speed. So in that case, we could think about it here in terms of periods, or we can look at it in this case, which we've had before, that the tangential was the radius times the angular. This is looking at it in terms of periods. Okay, for kinetic energy, when we talk about rotating objects, we know that regular kinetic energy is 1/2 mv squared. And we know that this velocity, this tangential velocity, is radius times my angular velocity. So I would do 1/2 m times this amount squared, which results in this equation. So that's one that we're going to use to find kinetic energy of rotating objects. So we can also write this as 1/2 I, and I is this moment of inertia times the angular velocity squared. And this I, if we go back here to this equation, we can see that I had mr squared. So that means mr squared is the same thing as my moment of inertia. And that moment of inertia, this is mass and this is radius, that moment of inertia changes depending on what kind of objects that you have. We looked at this last picture. This was mr squared. And that was in the case here where we have a hoop or a cylindrical shell. So depending on what kind of object you have, that I would change. So when we go back to this equation, this 1/2 I and then our angular squared. This I isn't always this. This I could be any of these depending on what kind of object you have. So they would have to tell you if it was a disk or a cylinder or a hollow sphere or a solid sphere. And then you could use the appropriate I. Now the total kinetic energy of a system is not only just the rolling object, but that means the linear and the rotational. Because not only is it going down, so it has some linear kinetic energy, but it also has the rotational because it's spinning. So 1/2 mv squared plus 1/2 I, which is our moment of inertia, times omega squared. So we can see that this whole equation can be simplified into this. And it maybe doesn't look a whole lot simpler, but it would be the same equation as this one. So the kinetic energy of a rotating object is a multiple of the kinetic energy, so here, this regular kinetic energy, plus then we have this multiple. And there are some where you have to find the kinetic energy. I think it's called kinetic energy of a rotating wheel. And when we talk about inertia, which is our next topic, we have two different objects and we want to know which one will reach the bottom first. So we want to think about in terms of the disk having less rotational inertia. And if we go back to all of our rotational inertias, this is our, we can have a disk which is 1/2 mr squared, whereas a hoop is mr squared. So this has 1/2 the rotational inertia, or that moment of inertia. And keep in mind, inertia is an object's resistance to move. So if we're thinking about rotating objects, the rotational inertia is its resistance to change the rotational motion. So if we have a big rotational inertia, that means it has a big resistance to change its motion. It's going to be harder to start and harder to stop. If it has a small rotational inertia, that means the resistance to change its motion is easier. So it's easier to start and easier to stop. So in this case, if the disk has less rotational inertia, then it would be easier to get it to change its motion. So that means it's going to speed up quicker as it's running down the ramp. And that one, there's a video tutor question about that last one. And I think it's called Video Tutor. And there is also one that's 10.78, which is dealing with rotational inertia, which is that last slide. Okay, then we get into the summary of Chapter 10, and it lists all the equations. So that's pretty much the lecture video for Chapter 10.